In this video, we're going to be looking at a past exam question which involves calculating and working out calculating and using a least squares regression line. The question is on the left-hand side of the page, and the formula that you will find in your formula booklet in order to calculate the regression line are on the right-hand side. So just to be clear, a regression line is the regression line y equals a plus bx is a straight line that best fits the data up above. So in the olden days, a long time ago, you probably would have called this a line of best fit, and this is sort of an actual mathematical equation for this line of best fit. So that's what we're going to do. We're going to work out what the equation of this line of best fit is, and the formula we're going to use, these ones on the right hand side. The key bits are we have to work out this value a, and that is given by y bar minus b x bar. Y bar is the mean of y, and x bar is the mean of our x values. And you should be familiar, so the mean of y is the sum of our yi's divided by how many there are, and the mean of x is our sum of our x values divided by how many there are, n. We also have to work out this value b, which is a little bit more complicated. So b equals sxy divided by sxx, which is the sum of xi minus x bar times yi minus y bar divided by the sum of xi minus x bar squared. Now these are very long involved formulas. They take a while to work out. Your calculator, most calculators with the stats mode can work these out for you. Save yourself a lot of effort. In this video we're going to go through it the long way, but it is definitely worth learning to use the stats mode on your calculator to make sure you can work this out more quickly with your calculator. I'm not going to do that in this video because it will depend very much on what calculator you're using. Because different calculators will have a slightly different method. Anyway, for our question, so the first thing we're going to work out are these y bar and x bar. Well, y bar is the sum of the yi's divided by n. Well, the y's are these values at the bottom, the time in minutes. So it's to work out y bar, we have to do 42.9 plus 40.6 plus 38.5 plus and so on. Divided by how many there are. Well, there's 9 different values, 9 different data points, so it's all divided by 9. And I'm not going to write it out in full, but if you do this in full, you should get 33 as your answer. We're going to do something similar for x. So x bar is going to be the sum of our x values, xi's. So it's 10 plus 12 plus 15 plus and so on. And again, divided by how many there are. Again, there's 9 x values. And if we do this sum and division, we get x bar is 20. Okay, so that's the sort of easier first step. Now we have to work out this sxy and sxx. Well, sxx, for each value of xi, so 10, 12, we're going to take away x bar and then square it. So we're going to do 10 minus 20. So 10 minus x bar and then squared. We're going to add that to 12 minus 20 squared and add it to 15 minus 20 squared. So what we're doing the sum of the xi's minus x bars. This is an even longer calculation. If you do this carefully, you get 386. Again, your calculator can do it more quickly in stats mode and just give you that answer directly. We'll do the same for sxy. So sxy is the sum of, so for each reading, we're going to take the xi and subtract x bars. So we do 10 minus 20, and we're going to multiply that by our y values, 42.9, take away y bar, so take away 33. and we're going to add that to, we're going to sum that over all our different data points. So we're going to do 12 minus 20 multiplied by 40.6 minus 33. And again, this is a much longer calculation. If we do this whole thing very carefully, I think we get minus 387.3. So that's the hard work, really. We're now just trying to plug these numbers into the formula into these two formulae. So I'll copy these formulae down. So B equals SXY over SXX. We worked out SXY and SXX already. So this is minus 387.3 divided by 386. And this turns into minus 1.003. And then A is y bar minus b x bar. It is 33 minus 1.003 multiplied by x bar, which is times 20. And this gets you to 53.1, I believe. So now that we've worked out what A and B are, then the least squares regression line is y equals A plus bx. We know what A and B are. This is 53.1. B is minus 1.003x. So this is our equation of the least squares regression line. It's a straight line with y-intercept 53.1 and gradient minus 1.003. So a downward sloping line. You know, if you were to plot this on a graph, it's going to be downward sloping with gradient 1, gradient minus 1, and it's going to intercept here at 53.1. And if you actually plotted all the data points, you'll probably get something that look like this. I don't know exactly, but this sort of shape, okay, is a best fit line of our data points. Okay, now if we look back to the second part of the question, estimate the time taken for the diluted dry when the air temperature is 21 degrees centigrade. So let's copy this down. So this is the good thing about the regression line. We can use it to estimate. So the air temperature is the x value. So in part B, when x equals 21, y equals 53.1 minus 1.003 times 21, and that gives you 32.1 minutes. So that's our estimate of how long it will take the diluted dry when the air temperature is 21 degrees. And that's the thing about regression lines. They allow us to make predictions. They're good when we're making predictions which are what's called interpolation. So if we're using a value of 21 degrees, which is sort of within the range of numbers of x values that our original data was. So our x values went between 10 and 30, so using a value of 21 degrees to work out the temperature is reasonable. What's called extrapolation is not necessarily reasonable. You know, you probably don't want to use this formula to work out the time taken when the temperature is 70 degrees or something way beyond the end of way beyond our x values, because we don't know that the trend will continue for much higher values of x. It might be that this trend that we've got here, it might be that when x gets really large, it actually flattens off. Probably not so sharply as I've drawn, but it might be that this trend doesn't actually continue. So yeah, that's called extrapolation, is when you sort of extend beyond the x values of our original data, which is not usually very reliable. In this case, fortunately, it's asked us to predict the air temperature when it's 21 degrees. And indeed, we can look at our value. We got 32.1. If we compare with the table, where we have values for 20 and 22, that's 33 minutes and 30.7 minutes. 32.1 is between those two values, so it does seem like a reasonable estimate. Obviously, that's all it is. It's just an estimate, and we've done nothing to work out how good a fit this best fit line was, but it still seems a reasonable answer.